Okay, let's dive right into this explainer and explore the fascinating, completely hidden systems flowing right beneath our feet. I mean, we walk over it every single day, we build our homes on top of it, and we literally rely on it to live. And yet, most of us never really give a second thought to the vast, invisible architecture of water hiding underground. It's an entire world that dictates the health of our environment, operating entirely out of sight.
So it starts with a pretty simple question. When you turn on the tap, where does the water actually come from? Well, to truly answer that, we're going to take a journey. We're going to go from the absolute micro level of a single drop of water, zooming all the way out to entire ecosystems. We're going to unpack the hard data, the continuous monitoring, and the real science behind our groundwater to understand just how deeply interconnected everything is. This isn't just about pipes and pumps, It's about the lifeblood of the land we live on. Section 1. The Hidden Water Table. To really understand our hidden water supply, we first have to explain the water table, because this is where we establish the baseline for absolutely everything. The water table is simply the boundary between water-saturated ground and unsaturated ground. It sits right above the zone of saturation. Now, in places like western Loudoun County, this geological system essentially has two main parts. Deep down, you have solid bedrock with these tiny fractures running through it, but right above that bedrock, you have the shallow soil, which hydrogeologists actually call saprolite. I really want you to think of this saprolite as a giant geological sponge. When it rains, this massive sponge soaks up the water, stores it, and then very, very slowly feeds it down into the deeper fractured bedrock. When a residential well is drilled, it pulls water from those deep fractures, but it's actually that shallow, unseen saprolite sponge resting above that keeps those fractures continually supplied with water year-round. So how are water levels determined if we can't just, look through the dirt? Scientists and local governments like Loudoun County and the USGS use a rigorous monitoring process. First, they drill dedicated monitoring wells. And just to be clear, these aren't used for drinking at all. Their only purpose is observation. Next, they deploy these highly sensitive automated pressure loggers deep down into the wells. These loggers take a precise reading every 4 hours, day and night, 365 days a year. It's a massive amount of data. Those readings are then calculated into daily averages so researchers can track the long-term trends. And finally, to ensure absolute accuracy and calibrate the instruments, technicians physically visit the sites biannually to verify the digital data with old-fashioned manual tape measurements. It's an exhaustive, constant process designed specifically to track the heartbeat of the aquifer.
Section 2. Cones versus capture zones.
Okay, we're zooming out now from the individual well to the neighborhood level to see what happens when we actually start pumping that water out of the ground. Whenever you pump water from a well, you create what hydrogeologists call a cone of depression. The drawdown contours form a very specific circular shape that gets deeper in the middle. It actually works exactly like a thick milkshake. When you draw the liquid up through a straw, the surface of the milkshake directly around the straw dips inward, forming a literal cone shape. Well, the exact same thing happens to the water table deep underground. As you pump your well, the water level in the immediate vicinity physically drops, sloping downward toward the intake pipe.
Now, what's really fascinating here is the crucial difference between that physical drop, the drawdown, and the actual capture zone. In hydrogeology, they are absolutely not the same thing. The drawdown, that cone of depression we just talked about, might only be a mile wide. It's the immediate physical dip in the water level. But the capture zone? The capture zone is the massive, three-dimensional volumetric flow path of water that is actually migrating toward the well to replace what you've just pumped out. While the physical cone of depression is very localized, the capture zone extending outward to gather that water can span for several miles. This means, without a doubt, your well is actively pulling water from far, far beyond your own property line. And that specific mechanism brings us to a staggering piece of data. In western Loudoun, over 90% of residential wells are located within 550 feet of each other. Let that sink in for a second. Over 90%. And almost half of all wells are within just 200 feet of one another. Because these wells are packed so densely, the idea of isolated pumping simply doesn't exist. Practically every single well's cone of depression is actively overlapping with its neighbor's cone of depression. Returning to our earlier analogy, everyone in the neighborhood is essentially drinking from the exact same, heavily interconnected milkshake.
Section 3. The purpose of hydro studies.
With all these overlapping cones of depression, how do local governments manage the addition of entirely new developments? Well, before a developer can build a new subdivision with 10 or more lots using private wells, they are legally required to conduct a hydro study.
So what is the significance of a hydro study? Think of it as a comprehensive stress test for the local aquifer. Environmental consultants come in, drill test wells, and run intense multi-day pump tests. Sometimes these tests run for 8 hours, and sometimes they run continuously for up to 72 hours, pumping water out at a constant, unyielding rate. During this time, they carefully measure the drawdown in both the test well and in nearby observation wells. The ultimate goal is to calculate if the local geology has the transmissivity, which is how easily water moves through the rock, and the storativity, how much water the rock can hold, to actually sustain a whole new neighborhood for decades to come. And looking at the map brilliantly illustrates the sheer scale of modern development. Every single one of those highlighted shapes and dots represents a specific hydro study parcel in Loudoun County alone. There are over 215 of these detailed reports currently on file. Each one of those marks is a detailed projection of future water demand. And remember, all of this massive new demand is being layered directly on top of the existing, already overlapping cones of depression we just discussed. It's a compounding stress on a hidden system. When the complex math from these intensive hydro studies is mapped out, it forms these concentric contours showing the predicted, localized water level drops radiating out around a proposed well system. Depending on the specific fractures in the local bedrock, the impact of a single new development can range widely. We're looking at a drop of a few feet to well over 50 feet of drawdown just at the outside perimeter of the site. And for the homes built directly inside that subdivision, sitting right on top of the pumping, the drop is projected to be even greater. Section 4. The safe yield illusion. But here is where we need to zoom out one final time to the macro ecosystem level. We really need to look critically at the primary metric driving all these development decisions. Many of these hydro studies calculate something called safe yield. Safe yield is a highly conservative engineering calculation. It relies on complex groundwater flow equations to predict exactly what will happen to the local water table if the new homes pump continuously for 90 straight days with absolutely zero rain or recharge during a severe worst-case scenario drought. Usually, they base this rigorous calculation on a standard withdrawal of 150 gallons per day per household. If the mathematical model shows that the well doesn't run completely dry under those extreme parameters, the yield is officially deemed safe. So, the crucial point is this. Safe yield is an excellent metric for guaranteeing that water comes out of a homeowner's tap, but it has massive, undeniable ecological blind spots. I mean, is safe yield truly meaningful if it completely depletes the surrounding natural environment? The safe yield math completely ignores the wider, miles-long tapture zone we explored earlier. When you pump an aquifer heavily enough, you can actually reverse the natural historical flow of the groundwater. Streams that have always been gaining streams, meaning the groundwater naturally flowed upward into them to keep them running during dry summer weather, can suddenly become losing streams. In a losing stream, the surface water is actually sucked downward into the depleted aquifer below. This actively diminishes the vital stream base flow that entire surface ecosystems desperately rely on to survive. To ground this theoretical reality in hard data, we just have to look at a recent USGS monitoring well in neighboring Fauquier County. In the summer of 2025, the water level in that specific monitoring well suddenly plummeted 25 feet. Why did such a drastic drop happen so quickly? Well, because a single new irrigation well started pumping just 300 feet away. When you recall the earlier statistic that half the residential wells in western Loudoun are within 200 feet of each other, a sudden 25-foot drop caused by a nearby neighbor shifts from a rare anomaly to a very real, very sobering threat to our water security. Section 5. Protecting our invisible resources. Let's tie all these invisible threads together. The cumulative data paints a very clear, objective picture of a highly stressed underground system. Remember that vital saprolite sponge we talked about at the very beginning? Because of densely concentrated increased pumping, the water table in many areas is actually dropped beneath the top of the bedrock layer. That means the shallow sponge is completely emptying out. As a direct result, drillers are forced to go deeper and deeper into the earth. And many new, low-yield wells now require a drastic process called hydrofracturing. That's where they inject high-pressure water to literally blast open solid bedrock fractures just to squeeze out enough flow for a household to function. Overall, the continuous monitoring shows a steady, long-term water table decline of 1 to 3 feet per decade in these heavily utilized regions. We've moved from the journey of a single drop of water to the reality of overlapping cones of depression, all the way to the complex, predictive math of municipal hydro studies. But the ultimate takeaway from all this objective data boils down to a fundamental question of balance. The hidden water flowing deep beneath our feet is deeply, inextricably connected to the streams, ponds, and delicate ecosystems thriving on the surface. So I leave you with this final thought. If our surface streams run dry and our environmental baseline fractures, can we really call our well yields safe? Thanks for joining me on this explainer. Keep questioning the world around you, especially the parts you can't readily see.